Astronomy Basics. Today we'll be talking about what is the universe's recipe for life? Where do the ingredients come from? We are all made of star stuff. These words were famously proclaimed by Carl Sagan on his TV show The Cosmos many decades ago. It was a statement that blew the minds of the viewers like me. I was made of long-dead stars. Wow. In fact, everything we are made of and everything around us originated somewhere out in space. We discuss the lives of stars in the terms of a life cycle, from birth to death and to new stellar birth. Here you can see the life cycles of stars. On the left you can see all the stars are born in a stellar nebula, also known as a stellar nursery. At the top is the lifeline of a star like our Sun, destined to become a white dwarf. Below is the lifeline of a massive star, and its fate after going supernova to become a neutron star or a black hole. The size of the star will dictate what elements it will create throughout its life, and then disperse throughout the universe in a planetary nova or a supernova. These elements from the dead stars are taken up in the births of new stars and are incorporated into the crusts of forming planets. Dmitri Mendeleev's periodic table of elements is not just a catalogue of all the elements. Taking a closer look, and we can find the periodic table charts the fundamental cosmic processes connected to the dawn of the universe and the lives of all stars. There are 94 naturally occurring elements in the periodic table, 92 of which are found in the Earth's crust. Technetium and promethium are produced in laboratories here on Earth, but have also been seen in the atmosphere of stars. Where do they all come from? Hydrogen is the first and the lightest of the elements in the periodic table. All the hydrogen that is in the universe was created in the Big Bang, the very beginning of the universe, along with some helium at a ratio of 75% hydrogen and 25% helium, and this ratio can still be seen in the composition of stars today. Hydrogen is not created in stars, so every atom of hydrogen the universe will ever have was created then in the Big Bang. Lithium, beryllium and boron were also created in the Big Bang, but in minuscule amounts, almost undetectable. Through their lives, stars perform the service of alchemy, whereby the material of the universe, initially simply hydrogen and helium, is steadily enriched with the elemental products of the previous generations of stars. What was nothing more than hydrogen and helium increasingly becomes other heavier elements, carbon and oxygen, silicon and iron, indeed all of the elements in the periodic table. From this chemical perspective we gain an appreciation for the life cycles of stars as living entities with a kind of cosmic purpose, a higher calling to create the very substances of life and the material world around us. So let us look at the periodic table of elements with fresh eyes. We will look specifically at the elements that stars produce that relate to us. Some of these are obvious, such as carbon as the basis of all life and oxygen as the stuff we breathe. Others will be less familiar, such as the vital importance of potassium neurologically and the surprising importance of various trace elements. Hopefully, through this tour of the elemental products of the stellar life cycle, you'll forever rethink the world around you at an elemental level, specifically in reference to what stars make. When we see the world this way, then our intimate connection to one another as inheritors of the chemical legacy of the stars becomes clear. Let us start by looking at the periodic table, and let's do a simple division of the table into 4 broad groups of elements based on the stars. The first group of elements would be the first 5: hydrogen, helium, lithium, beryllium and boron. These are the elements that came to us from the Big Bang. In fact, most of what the Big Bang delivered were just the first 2 of these 5 elements, hydrogen and helium, in a proportion of roughly 75% and 25%, with just a smidgen of the other 3 elements. Consequently, hydrogen and helium are the most abundant elements in the universe, and in all stars appear in approximately the same proportion. Stars do not make lithium, beryllium or boron, because making them from helium would actually represent a loss of energy for stars. This happens because the bonds holding the nucleus together are weak, and so this allows these elements to break down into the lighter elements. We can use the so-called binding energy curve to see why this is, and that's what you're looking at now. Fusing heavier elements from lighter ones generally produces energy in the process, but only if the product of the fusion is higher up on the binding energy curve than the element that went into the fusion, and lithium, beryllium and boron are lower on the binding energy curve than helium, hence the energy loss to the star. The second major group of elements is actually just one: carbon. This is the element made by relatively low mass stars, stars like the Sun, and when they near the ends of their lives, that to become red giant stars. This is as far through the periodic table as a low mass star like the Sun will get before ending its life as a planetary nebula and leaving behind a white dwarf corpse. The third major group of elements includes the elements from nitrogen through to iron. These are the elements that, in addition to carbon, higher mass stars produce through their lives as they proceed through successive rounds of fusion, creating successively higher elements than from the lighter ones. As they more and more desperately try to extract additional energy to hold themselves up against gravity. Remember that the heaviest elements a massive star may produce before it finally dies in a supernova explosion is iron, because that is the heaviest element that may be fused from lighter ones and produce some amount of energy for the star. The final major group of elements heavier than iron. These are the elements that cannot be forged by the stars during their lives. However, in the fiery depths of massive stars as supernova, releasing all at once more energy than all the stars in the galaxy shining together, an abundance of free energy permits these energy-costly elements to be forged in a flash. By the way, even though we've included the noble gases in these groupings, in fact, we will mostly ignore those elements here. That's because the noble gases, also known as inert gases, cannot form compounds. These elements always exist as isolated elements even when in the presence of other elements or compounds. For example, in Earth's air, the element argon makes up about 1%, but it doesn't do anything. It doesn't combine with anything. What elements make up the recipe of life? The most important ingredients are carbon, nitrogen, oxygen and hydrogen. We also need a handful of other ingredients in smaller amounts, but these are nonetheless crucial to the success of the recipe. Calcium, sodium, sulfur, chlorine, phosphorus, potassium and iron. Finally, we need smidgens of trace elements that are the spice of life. These elements are copper, zinc, selenium and cobalt. The main ingredients. The ingredients that we would mainly require are hydrogen, carbon, nitrogen, oxygen, calcium, sodium, sulfur, chlorine, phosphorus, potassium and iron. These elements make up almost everything around us and are the bulk elements of our body. Sure enough, aside from hydrogen provided by the creation of the universe itself, these are the elements that stars cook during their lives. All living things on Earth have just 4 elements in common: carbon, nitrogen, oxygen, and the hydrogen that bonds to them. Ignoring helium, those 4 elements are the 4 most abundant elements in the universe. Hydrogen is about 75% of all matter, a direct inheritance from the Big Bang. Carbon is made by all stars, including massive stars, as one stage of fusion, and by lower mass stars as the final stage of fusion before their deaths. It's the one element, helium aside, that every star in the universe will manufacture, so no wonder it's so abundant. With carbon being so abundant, and also it makes sense that just about every living thing the universe might create will not only involve it, but also use it as a base ingredient. Nitrogen and oxygen are the first elements after carbon to be fused by massive stars, and they are also the elements that, after carbon, provide stars with the most oomph in the form of additional fusion energy. So it's not surprising that these are the next most abundant elements in the universe. It's no wonder that life the universe was to cook up will include these ingredients also in good measure. Carbon is the backbone of all life. From the spiral lattice of DNA to the basic structure of proteins, carbon is the base, the foundation. Every cell of every living thing has it. It is in a very real, physical, literal sense what you and I are made of. When plants perform the magic of photosynthesis to grow the biomass of their bodies, what they are doing is taking in carbon dioxide from the air and using the energy of sunlight to incorporate the carbon from that carbon dioxide into their bodies and to return the oxygen back to the air. When animals consume these plants, they are incorporating the carbon that the plants took in from the air. Then, when carnivores consume these animals, they are, in turn, taking in that same carbon and incorporating it into their bodies. Chemically speaking, we are not that different from a lump of coal. What is an enormous sprawling oak tree made of? It's made of carbon. Carbon that the tree has sucked in from the air and has bound to itself with the energy of sunlight. Burn that tree and the fire produces that same sunlight energy pouring back out. Those carbon atoms, every last one of them, came from a long dead star, sprinkling its ashes into the cosmos. Those dead stellar ashes now make up the atomic level, the fibre of our beings, stellar ashes held together by the energy of the sunlight. But if carbon is the foundation of life, oxygen is what propels it. Oxygen has the uncanny ability to react with just about any organic compound, meaning any compound containing carbon. And these reactions are the essential functions of life, including respiration, which is, as you probably know, involves the taking in of oxygen and the exhalation of carbon dioxide. Oxygen bound to carbon. This is a diagram of cellular respiration. Glucose plus oxygen equals carbon dioxide and water. But what about nitrogen? It is made in stars through the fusion of carbon and hydrogen. Nitrogen you may feel less connected to this essential element, but in fact it's everywhere. Perhaps the most common and important form of nitrogen is in ammonia. That's one nitrogen bound to three hydrogens, which is in the main ingredient of fertilizer. Prior to the large-scale production of ammonia-based fertilizers in 1940, farms routinely rotated out crops like corn for crops like alfalfa or beans that could return nitrogen to the soil, as needed by these important cash crops. But with the invention of ammonia-based fertilizers, the ability of farming, and in particular the large-scale production of corn and grains, has revolutionized agriculture. So while our bodies don't make use of hydrogen directly, it is central to many of the processes by which our most basic carbon-based foods grow. Here you can see the nitrogen cycle here on Earth, and you can see how man-made fertilizers and animal fertilizers help produce our crops. Other crucial ingredients. Next on the list of ingredients are the elements calcium, sodium, sulfur, chlorine, phosphorus, potassium, and iron. Calcium is an essential component in human bones and teeth. Calcium also plays a very important function in signaling within our cells, helping to regulate the action of nerves and muscles. That signaling is so important, in fact, that the body will sooner dissolve the bones than permit calcium levels in the blood to drop too low. So indeed, that white chalky substance scratching out the formula such as E equals mc squared on the chalkboard is a highly essential ingredient in our recipe of life. Next up is sodium. We immediately associate sodium with salt. Every atom of sodium in the universe was made in high-mass stars through the fusion of two carbon atoms. In our bodies, sodium is an essential nutrient that regulates blood volume, blood pressure, fluid equilibrium, and pH balance. The human body must have at least 500 milligrams of sodium per day to function, with a recommended amount of 2 or 3 grams per day. Sodium is also a critically important component of neuron function in our brains. Hypothermia is a condition in which sodium levels in the blood drop too low, and one of the main symptoms is confusion and disorientation. Without sodium we cannot think straight, let alone ponder where we come from. We need stellar ash in our brains to contemplate the stars. Phosphorus is, after calcium, the most abundant element in the human body. Most of it is locked up in our bones and teeth, where it helps form a protective enamel layer. But a tiny bit of it is also so essential that life as we know it simply would not exist or function without it. Phosphorus is required by all known forms of life. It plays a major role in biological molecules like DNA and RNA, forming a part of their structural backbone. Importantly, phosphorus is also the key component of adenine triphosphate, or ATP, in which a group of 3 phosphorus atoms provide the molecule's key features and functions. You probably recognize ATP from what we've learned about how biological processes use and store food for energy. Nearly every cellular process that uses energy obtains it in the form of ATP. Phosphorus is also one of the key components of all cellular membranes, which separate and protect the cell from its surroundings. Every atom of phosphorus that exists was made in massive stars through the fusion of silicon and helium. Potassium is the next most abundant element in the body. Massive stars make potassium through the fusion of 2 oxygen atoms. Every atom of potassium in the universe was made this way. In our bodies, potassium is crucial for proper nerve transmission. Without enough potassium, fingers freeze up and eventually cardiac arrest follows because the heart's beating function is regulated by this important element. Sulfur is made in massive stars through the fusion of silicon and helium. Because of its nasty smell, it has throughout history been associated with hellfire burning. However, we cannot live without it. Sulfur is an essential component in all living cells. It is present in all proteins and enzymes that contain certain essential amino acids. Pure chlorine is about as horrific a poison substance as you could imagine. A whiff of pure chlorine gas is like a blast of a blowtorch to the sinuses and lungs, and breathing more than just a small amount of it can cause death. But together with sodium, chlorine forms regular table salt, and in our body, chlorine serves an important role in nerve signaling and digestion. Now we come to iron. Iron is the heaviest element that massive stars produce before they explode as supernovae. Every atom of iron in the universe was smelted in the crucibles that are the cores of massive stars in the final dying gasps of their lives. Iron is abundant in biology. Iron-based proteins are found in all living organisms, from the evolutionary most primitive right up to us humans. The color of our blood is due to hemoglobin, an iron-containing protein. Iron, together with sulfur, is found pervasively throughout our bodies, especially in enzymes, responsible for many cellular functions. Perhaps most importantly, the transport of oxygen in blood to cells throughout our bodies. In fact, the major theories of evolution invoke this iron sulfides as a fundamental driver of the evolution of life on Earth. Iron atoms sprinkled through the galaxy by supernovae explosions, spreading their dead stars material up through the galactic geysers and across the galaxy, are stellar ashes which make up our lifeblood as well as the most massive and substantial products of human ingenuity. Now we come to the spice rack. These are the trace materials that, used in pinches, make up a tiny but nonetheless crucial part of the overall recipe. Indeed, life depends on smidgens of certain rare elements: copper, zinc, selenium, and cobalt. These elements show up in our hair and blood. These are the elements that stars forge in their fiery deaths. The first element in our spice rack is copper. In our bodies, just a trace amount of the stuff, about 2 parts per million, is crucial for proper iron uptake. And because iron is so important in our blood, copper deficiency can in turn lead to anemia-like symptoms, bone abnormalities, osteoporosis, and impaired metabolism. Another essential trace element in all animals is zinc, which is a component of hundreds of different enzymes. There are just a few grams of zinc distributed throughout the adult human body. Most of it is found in the brain, muscles, bones, kidney and liver, with the highest concentrations in the prostate and semen. There may be no other element produced in the fiery supernova deaths of stars that is so intimately connected with the conception of new human life. In addition to copper and zinc, the element cobalt is essential to all animals. It is the key constituent of cobalamin, also known as vitamin B12, which is essential to the health of our nervous system. It is made by bacteria in the guts of ruminant animals, which convert cobalt-based salts into B12. The final element is selenium, which makes up less than 0.01% of our body mass, but plays an important role in the functioning of the thyroid gland and in every cell that uses thyroid hormones. So, we have our shopping list of elements to make life, but where do we find them? Hydrogen is essentially free, having been provided by the Big Bang. Every bit of carbon in the universe requires a star. Stars like our Sun make carbon as red giants shortly before their deaths as planetary nebulae. Nitrogen and oxygen require massive stars to fuse them from carbon and helium atoms. These are the main elements that stars make, so our universe's pantry has them in relative abundance. Every single atom of calcium, sodium, sulfur, chlorine, phosphorus, potassium and iron comes to us from the later stages of fusion as massive stars fail to keep themselves alive in their dying breaths. The stars don't get much bang for the buck with these stages of fusion, so they produce them in relatively smaller abundances than carbon, nitrogen and oxygen. As for the spices, these are rare elements and can only be obtained from very special places, the fiery supernova that are the violent deaths of massive stars. These elements are flash-forwarded in just an instant, and very little of them is produced. Indeed, these are rare spices, but without their seasoning the recipe of life will fail. The stars, in both their lives and deaths, make every element in the recipe of life. Through their deaths as planetary nebula and supernova, they blend these ingredients throughout the galaxy. These elements that will then seed the atmospheres of the next generations of stars at their births, or become ingredients in the makeup of the crusts of new planets. We are made of the stars. We breathe them, we consume them, they course through our veins and we tingle with them. We live on a world made of them, and we move through a material world built of them. In our contemplations of the stars, in our comprehension of them, we are, in essence, the stars contemplating and comprehending themselves. Well, thank you for listening to this Astronomy Basics, and I hope you found it enjoyable. I would just like to leave you with one thought. We have learnt that all the hydrogen in the universe was made at the moment of the Big Bang. Hydrogen has a big place to play in the makeup of our bodies. It's locked in the water and it's locked in all the enzymes and everything else that courses through our veins. So, if you think about it, atoms within inside your body right now are as old as the universe themselves. That is 13.8 billion years old. Don't you find that amazing? Anyway, thanks for listening. Bye for now.